one example down, let's revisit our other example of these Riemann sum estimates for definite integrals. So we were looking at the quadratic 5 minus x squared running over the interval from -1 to 2. So let's go ahead and set the stage for this thing. So b minus a over n, my b is 2, my a is -1. So apologies for the small handwriting, but 2 minus -1 is going to give me a 3, so I have 3 over n. My x sub k is going to look like a, which is -1 plus k times that delta x we just came up with, 3 over n. Or if we rearrange this a bit, I like writing it as 3k over n minus 1. If you wanted to leave it the other way around, that's fine. It just ends up feeling a little weird to me when we start filling stuff into this function momentarily. All right, digging into the big guy. So we need a limit as n goes to infinity of the sum as k goes from 1 to n. We take this guy, he gets fed in here, so we have 5 minus 3k over n minus 1 quantity squared. And I'm going to go ahead and erase my x sub k formula here just to clean this up so I don't awkwardly have to write the delta x in inexplicably tiny font next to it. So now, algebra time. So the limit as n goes to infinity, the sigma bit looks the same. So when I work through this, foiling out 3k over n minus 1 quantity squared is going to give me 9k squared over n squared when I multiply the first terms. I'm going to have 2 copies of negative 3k over n, so minus 6k over n, -1 times -1 in the back gives me a plus 1. I still got that 3 over n dangling around on the end. All right, I'm going to have to distribute the minus sign. Don't overlook that. That will throw things off pretty severely. All right, so in the interest of conserving board space here, I am going to try to collapse these two guys together. So I'm going to distribute the -1 and then the 3 over n all in one burst. So hopefully, you can follow along with that. So for what it's worth, 5 minus 1 is going to be 4, and then 4 times 3 over n is 12 over n. And again, if you need to walk through each of those steps separately, that's fine. I don't judge. So we'll have minus 9k squared over n squared times 3 over n. So that's 27k squared over n cubed to the third, minus a negative 6k over n, so plus 6k over n, times 3 over n. So that's going to give me a plus 18k over n squared. Got to be very careful that I don't overlook a factor of n or something, because it'll grossly throw stuff off. So now, this is the guy we got to deal with. All right. Those jump cuts are kind of tingly. Anyway, so I've gone ahead and taken the liberty of breaking this summation up into separate pieces across the subtraction and the addition, pulling out the stuff that doesn't depend on k. So we have 12 over n sitting inside this first guy. We've got a k squared here, and then a k. So we're going to need 3 of our summation formulas from our handout. So, all right. So the first guy is a constant. We just take the constant and multiply it by n. Make sure that's clearly a multiplication. There we go. So the next guy is k squared. We haven't used him yet inside here. So we have n times n plus 1 times 2n plus 1 all over 6. That's uncomfortably long here. So anyway, I'm just going to write this next term down below. So we have 18 over n squared out front of this guy. The formula for summing up k looks like n times n plus 1 over 2. Close my bracket. Let's clean this up before I have to erase the board again and see what we end up getting left with. So just like with our last example, those n's conveniently go poof. This n goes away. That's going to drop down to an n squared. squared in the bottom, this would cancel because it's divisible by 3. So I've got a 2 here. This would give me a 9 because 27 is 9 times 3. Here, I have a 2 on this term and an 18 up top, so that gives me another 9. He goes away entirely. And in here, one of the ends in the bottom. All right, so now I've got this stuff roughly cleaned up. I took the liberty of cleaning this up a bit so we don't have all those awkward slashes all over the place. Okay, so our first term here is 12. There's no n, so it's not going to care what happens as we take a limit. Here we have another rational function. This time around, our high power terms still match up. They're both squares, so we're going to need that ratio of leading coefficients. Same thing here. We've got an n to the first, n to the first. So leading coefficient over leading coefficient. All right, first guy gives me 12. All right. Here, if you need to distribute these things, that's fine if that makes it cleaner for you. I usually just kind of remember that the constant is along for the ride and then attach it to whatever is sitting in front of that guy. So we have 9 times 2 up top. The coefficient of n squared down below is 2. And back here, the coefficient of n up top is a 9. The coefficient of n down below is a 1. If you had just written 9, I get it. Anyway, now we clean up the arithmetic. Slash, slash. 2 divided by 2, they cancel, so we have 12 minus 9 plus another 9. So we have a limiting value, a definite integral value, an area, however you want to describe it, of 12. So there's a lot of algebra here. I wish I had some way to sugarcoat that, but yeah, we really do have a lot of algebra we work out here. Sometimes I heard someone say a long time ago, the calculus is easy, it's algebra that's hard. Sometimes stuff like this really does feel like it backs it up. The limit wasn't anywhere near as intimidating as trying to get to the point where we had a thing for which we could take a limit. You may be a little concerned at this point. So each of these examples ends up taking up quite a large amount of board space, quite a long amount, time-wise. Is this all that remains for the semester? Really, really long single calculations to get at stuff for relatively straightforward functions. And you may already be looking ahead to, like, dear, merciful maker, what happens if we've got a trig function or a log or something like that floating around in these things? So we could delve into that. That's not where we're going. Take a deep breath. Okay, so there's a light at the end of the tunnel. I have done this long enough. I can tell you it is not the headlamp of an oncoming train. We've got a way to get around this. We're going to get there. That's the next section.